Have you ever wondered what's under your bed? Well, I've got the perfect tools for you. Not only can you use this spy robot to make sure you don't have anything lurking down there, you can also use this bracelet to defend yourself in the case that you do have unwanted guests.
Oh my god.
In this video, we're going to create the electronics, the battery, and the trigger for this spray bracelet. And we're going to have a special guest. By the end of this video, we're going to test a complete and fully functional device ready for a very modest amount of action. In the last video, I showed a few designs for printed circuit boards, or PCBs, that allow me to combine my typical electronic modules together in a neat and tidy way. These modules being a microcontroller, an H-bridge, and a voltage regulator. These components are so universal for me that I'll use them in Charlotte, my 8-legged robot, and in my cable shooter, and in my little Spraycelet here. Anything that requires a little bit of moving and a little bit of thinking. I'm happy to report I got PCBWay to manufacture one of these designs, and we're going to see if it works. So here's the whole mount board that I got PCBWay to make for me. It's my own design. I have no idea if, for instance, these traces are too close together, or too far apart, or too thin, or too thick, whatever. I don't know anything really about PCB design, except for, what needs to connect to what. So I have no idea if this is going to work. I've made the high current traces a little bit wider. That's just a general principle, I know. There's a lot that this board can include. You can see we've even included the Zener diodes and the resistors and the LED for the low voltage battery indicator. This low voltage battery indicator circuit is something I demonstrated 2 weeks ago for my gripper. I used Zener diodes with voltages of 5.1 and 6.8 to have an LED turn on only when the supply voltage is less than 10 volts. For the bracelet, I'm interested in a 7.4 volt nominal supply, so I chose Zener voltages of 3.9 and 4.3 so that the LED turns on only when the supply voltage is less than 6 volts. So yeah, we're going to put the QT Pi and the voltage regulator and the H-bridge onto this PCB, solder everything in place, and then just see if it works. Since the test version of this design has female pin headers to fit the 3 modules, the resistors can always be added or modified as needed. For now, I'm just adding the constant resistor that forms our voltage divider alongside our force-sensitive resistor, or FSR, trigger. Speaking of which, why do we need a voltage divider for an analog sensor like this FSR? Well, it just makes sure our sensor reading is always predictably some voltage between 0 and the digital voltage, which is 3.3 volts for the QT Pi. The value of the constant resistor changes the sensitivity of the resistor. Look here. When we plot the common formula for this voltage divider as a function of the sensor resistance, we see how the analog signal voltage changes. The slope of this line is called the sensitivity. Now, I'm not taking into account how the sensor resistance changes as a function of the true stimulus, the force applied on the FSR. This is assuming linearity, which is almost certainly not the case. In any case, you can see how changing the constant resistor value shifts these graphs. This is a difficult thing to optimize in the way I did my valve mechanism because it largely depends on that unknown function of the true stimulus, which is something I could measure, but I found most values of resistors work quite well, especially since I'm just using these FSRs as essentially a glorified flat switch. It would largely depend on your application, but if you wanted to optimize your resistive analog sensor, this is a good place to start.
Yeah, but you have the calculator ready, I bet.
No, I don't. I did that in my head.
Whenever you start using bigger numbers, that's when you have to pull a
You
calculator
don't need a
out.
calculator for everything.
I knew these dividers would be necessary for analog sensors, so I built 3 right into this PCB, so I can just connect whatever analog sensor I need across any of these 3 whole pairs. After soldering everything to this board and adding removable modules, it was time to test. And it worked just as our breadboard version did. You have to understand, this is really exciting for me. I've never used a custom PCB for my projects before. Typically, it's these really rough proto boards. I've saved both headache and footprint by doing this. Given it's my first time, I wasn't really sure if it was going to work, but it did. Thanks PCBWay for a job well done. In KiCad, all I had to do was select the PCBWay plugin, which sends my design right to PCBWay, and then it auto-detects everything. I just need to select colors and thicknesses and materials, and that's it. You can visit the link in the description for $5 off their obviously pretty impressive services. Now, I also have a permanent version of this board that's derived from the same PCB. I simply don't add header pins and solder my modules directly to the board. This reduces the space the electronics take up, which you can imagine is pretty important for a project like this. This does mean I need to decide on all the resistors for the support circuits beforehand, since they'll be hidden under the modules. These boards are pretty customizable when it comes to the pins that are not being used on the QT Pi, but I've added the support circuits for 3 analog sensors, those being the voltage dividers we discussed, and support circuits for digital output devices like LEDs, which may or may not require series resistors. For the voltage dividers, I've chosen to attach 2.2, 5.6, and 10 kilo ohm resistors. And for the series circuits, I've added 2 0 ohm resistors, or essentially jumpers, and 1 220 ohm resistor, and 1,000 ohm resistor. Alongside this permanent version of the circuit board, I wanted to immediately make the compartment that attaches to the bracelet for the permanent electronics. So you can see here we have this circuitry compartment here that can store all of the electronics. We have a pretty nifty fit for our permanent version of the whole mount PCB. And you can see I've already attached the battery connectors and the power switch, and those are already attached to the board. Pretty convenient. This permanent board has a lower profile than the temporary board for sure, but you can see these capacitors on top of the H-bridge module. They do stick up quite a bit. So you do have to account for quite a bit of space, but I still was able to fit them pretty snugly inside. Now, in addition to this circuit board compartment, I did want to do a quick redesign of sort of the main attachment frame. And this is the part that interfaces with our pressure vessel here, but it's also going to need to attach to our circuit board compartment. And that will attach sort of just like this. So this is supposed to be attached with 3 flathead M4 screws. Yeah, it seems to work pretty well. You can still slide this in, just like that. Very nice. So I also, did a quick modification to this frame because I needed some more space for the motor. I had to kind of shave off some material last time, but this time I think it should be a good fit. Oh yeah, that fits much better for sure. This circuit compartment comes with a little handy lid. Seems to fit quite well. All right, and now we have the complete electronics module added to the back of this pressure vessel to form a full bracelet, except for we still need a way to power this. You can see I've added the ports to the batteries back here, and we need to design a battery pack that fits into this and also snaps into place. I've been doing a great job so far with my bi-weekly Friday 5 p.m. schedule, which is tricky since I'm actively working on my PhD. For more frequent updates, follow my Instagram at the.amazing.labs. If you want to help me continue innovating, support me with just $1 per month at patreon.com/theamazing. Or I accept one-time donations via PayPal at the email draglinedynamics@gmail.com. You can also book an inexpensive tech consultation or tutoring session at my company's website, dragline.tech. And remember, all you have to do to support the channel is subscribe. In case you missed it, be sure to check out me risking my life on my repelling invention and my octopod, Charlotte.
Did someone say my name?
Charlotte, why do you sound like Siri?
Who?
The voice from the... Never mind.
Just saying I haven't been in a video in a while.
Sure you have. You're in the background sometimes, just sitting there, you know.
Okay, but you haven't upgraded me. Look at these stupid ass wires coming out of my back, and I still can't walk right. When I was the focus of videos, they did pretty well. You have this fancy looking circuit board, why can't I try that out? You're giving all that attention to your damn jewelry.
Okay, fair enough. I said these circuits were universally useful, and I meant it. I'm going to give Charlotte here a few upgrades, and give her a little more control over herself by adding my custom PCB. And look, if you haven't seen Charlotte before, just know the main cool thing about her is her legs are all single prints, made from multiple materials in the form of both soft and hard TPU, or thermoplastic polyurethane. If you need to know more than that, I have great news. These videos are free to watch. Upgrade 1. The last iteration of Charlotte you all saw still had some undesired compliance in the legs, so I've added this constraining device to the proximal links to stop them from twisting, making sure this 4-bar linkage is a planar mechanism only. Upgrade 2. Previous versions of Charlotte all relied on press fitting to keep the legs attached. This didn't always work so well, so I added some screw holes to both attachment points to prevent legs from falling off. Upgrade 3. Previously, Charlotte was heavy.
She weighs like 180 grams or so.
This is because she had 4 motors, when I really only need 2, one for each side. So I found these gear motors which are smaller, require a lower voltage, and can output more torque. This does mean she's going to walk slower, but I'm excited to see the gait cycle in slow motion. Hopefully she's actually walking and not just dragging her belly on the ground like before. I can always upgrade the motor speed later. Upgrade 4. I also made sure the hard TPU covered both sides of the leg, all the way up until the very tip of the foot, so I can make sure I have the higher friction coefficient afforded by the softer material. As many comments on my original Charlotte videos smartly pointed out, friction in the feet is of course absolutely necessary for walking. This is something I sort of overlooked in my previous design. And of course, I am giving Charlotte a battery and my PCB controller. I'm just going to use the test version from our previous experiments, since I already have it. All right, so here we have the new and improved Charlotte design, complete with the electronics on top. You can see I've just added sort of 2 little baskets here to hold the batteries. So I don't really have the means for remote control right now, so I just added this switch here so I can change between sort of forward and turning and reverse modes. Now I can attach the QT Pi now, but before I do that, I'm actually going to go write the code for this design, just so we can do some fundamental tests of Charlotte's mobility. But right off the bat, from a mechanical standpoint, she can actually stand up now in a stable way. Her belly is not dragging on the ground, so hopefully that continues while she walks. Here's the side view. You can see she's standing on 4 legs, complete stability, no buckling. She's got even a good amount under her. So yeah, not close to the ground at all. It looks quite nice. I'm excited to see her walk. So let's go program this QT Pi so that we can finally see how this new and improved Charlotte moves. So here's the code that we're going to upload to Charlotte. I'm using the NeoPixel, which is the LED, the multicolor LED on the QT Pi to sort of indicate which mode we're in. We've defined our button pins and all 4 pins, that's 2 for each motor, for the H bridge, and we have a bunch of variables here, and I basically just have functions for what the pixel should be, and I have functions for what the motor should be doing, whether it's forward mode, backward mode, right mode, left mode, or off mode, and I have a function to change the mode, which gets called if the button has been pressed. So it's pretty straightforward. We're going to go ahead and upload this to our Qt Py and plug it into Charlotte. All right, here we have the complete Charlotte with that code uploaded, and we're going to see if Charlotte works. First time untethered. I didn't add a power switch for this one, so I'll just connect the batteries. Okay, so that white light came on just like we wanted. So we can use this switch to change modes. And we're walking forward. Change again. Do a left turn. Go backward. Do a right turn. Wow. That's awesome. Whoo! And then white is stop.
So she's obviously slower than she was before, but it's nice to see actual walking instead of scrambling. And I'm sure the speed can be fixed at some point in the future. I love the turning. The turning is so much fun. Reverse. Turn again. Wow. That's so much fun. So she is very mobile. That's exciting.
I'm pretty happy to see Charlotte walking around, better than she ever could before.
Thanks, Will.
No problem, Charlotte. I think she's almost ready for sale.
What?
Oh, well, I just...
I'm just kidding. I know I'm a product. I can't wait to be sold. I'm gonna help save the world.
Keep telling yourself that. That was a skit. Charlotte can't talk, nor does she have consciousness. I'd like to show you guys my design for the Bracelet's battery pack. And my idea is basically we want to have that 7.4 volt power supply. So I use two 3.7 volt LiPo cells, lithium polymer batteries. I've designed this cool part that has built-in leaf springs here, so I can just slide this in and it sort of just press fit into there. So the lid fits on like that. And I'll have some high friction stuff to keep these clamped and sort of straight on like this. But the reason I'm doing this is so that these cells inside this battery pack are independent. They're not in series. Inside the bracelet, I'll have the series connection for these cells. I also designed this to match this charger for these independent 3.7 volt cells, but I can just connect the charger like this, and these cells are charged in parallel. So it's essentially balance charging, and balance charging is really important for LiPo cells because you want to make sure that they all are charged sort of at the same rate. Usually you have a balance charger like this, and this works with the sort of batteries that I used in the gripper, which are sort of cells that you find that look like this. The use of multi-cell batteries like this with balance charging and having a charger like this is really inaccessible unless you have your own charging circuit. That's why these are really used for like hobby electronics and that sort of thing. So I've always been trying to figure out ways to make the battery storage for my inventions a little bit more accessible from a product standpoint. And oftentimes you'll see I've used 9 volt batteries and that sort of thing. This is another way of doing that. Independent LiPo cells that can be charged with an accessible device like this. Another thing I wanted to do with this battery is to have it able to be clicked into place and then easily removed. So I have these little spring pegs here that I can attach to the battery pack, and these will allow the battery to be clicked into place, and then you just press on this from the outside so that it can be easily removed. So here's the final battery pack. You can see it has these pegs here to snap it into place, protruding connectors that mate perfectly with the back of the electronics module here. And we can try to connect it together, see how it works. All right, snapped into place. Very good. Now we got to see if it works. All right, you can see LED turn on in there. And we have that same code running. FSR is working, motor's working, so it's all working. That's great. We just need to add the firing mechanism here to connect the motor to the valve. That's pretty simple, should be pretty straightforward. I'm very happy this worked on the first try. All right, I think it's working. Nice. Another thing I want to do is see if there's a way to have some kind of mounting for this trigger so it's not just loose. I kind of want it to just stick out here and then have something with sort of semi-rigidity keep it here so that it's like nicely framed on the palm. Yeah, I want to see if I can build something like that.
So there you have it, a fully untethered wearable spray bracelet, which you can fill with your fluid of choice. It works great, it feels great, so it begs the question, what went wrong? I'm proud of this prototype as is, but I must admit, the size of this thing got away from me pretty fast, especially with the electronics and the battery. It's got some bulk, sure, but I promise you, this is progress. Longtime viewers remember my old method of having separate modules around the wrist for microcontrollers, drivers, and mechanisms with a mess of wires wrapping around every component. This has all of that on a single circuit board, without the wires. I've just got 2 wires leading to the motor and 2 wires leading to the trigger. I used to think this design had a small electronics module, but this new PCB dwarfs that. And the new battery is comparably compact as well. This design was powered directly from my Suit's power pack, and this design had an external battery that you see here. Then there's the storage. This design can hold around 30 milliliters of fluid, just around the wrist. That's what I used to store up here on my upper arm. So even though it may look bulky, this is hands down the most self-contained version of this I have ever built. That's not to say I'm not committed to slimming it down even more. I'm a big proponent that technology is always miniaturizable. It's important for Charlotte too, since I hope future versions of her can become indistinguishable from real spiders. There are smaller batteries for sure, and smaller versions of this pressure vessel, but I also have a smaller design for the electronics. This new PCB is soon to arrive and contains everything within the regulator, H-bridge, and microcontroller directly surface mounted on the board. I'll talk about that design in 2 weeks, on April 18th. Stay amazing, and I hope you'll join me as we continue our journey to generate new technologies and seek to make them always just a little bit smaller.